Hey, welcome to the last video of this section, Securing Docker Containers. In the previous video we had an overview of the libvirt architecture. In this video we'll first learn to align Docker security with svirt and to limit container capabilities. We'll also see how to relabel volume mounts. A new type of virtualization has been gaining traction, called containerization, more specifically Docker containers. When working with containers, administrators have to be well aware that containers do not virtualize everything. The Linux kernel itself is shared, and all software running inside the container is interacting with the Linux kernel, just like software running outside the container. That does not mean that containers don't isolate, though. They're built based on Linux features such as namespaces and control groups. As the Linux kernel is shared, exploits on the kernel level impact the entire host and can compromise not only the container through which an exploit is executed, but also other containers and software running on the host. Generally, one could imagine using SELinux to prevent vulnerabilities to be exploited. Policies could be used to ensure that software running in the container cannot perform any action that is not acceptable behavior for that software. However, as the Linux kernel is shared, containers have a different approach to SELinux support. While full virtualization allows the guest operating system to use SELinux as well, containers do not have this luxury. Right now, if in-container software checks whether SELinux is enabled, it receives a disabled status, even when this is not the case. The reason behind this is that SELinux itself is not namespace aware. While namespace isolation is the key part of containers on Linux, SELinux is part of the Linux kernel, and the policy is applicable to the entire host. As long as SELinux does not support policy layers and namespace-aware access controls, we'll need to deal with SELinux on the host level only. When the Docker installation is one that doesn't use svirt technology, then containers will run through the Docker for container runtime T-type, which has but a few handles that administrators can tune using SELinux booleans. The important SELinux booleans that influence Docker T access controls are listed on your screen. Docker has a similar approach to virtualization as most other hypervisor-like solutions. It has a management component, or the Docker daemon, and runs guests in which the container software runs. The guests here are processes that enable new namespaces, hiding the host-level view of files, processes, users, and so on, and run the container software as sub-processes. By default, Docker does not have the svirt technology built in. This means that when running Docker on an SELinux-enabled host, the processes that act as the containers will run with the Docker T-type, the type used for the Docker management daemon. And often, this works just as expected, but does not isolate the guests much. Red Hat is adapting Docker to support the svirt principles. When running with Red Hat Docker, new guests run within isolated domains and receive a set of MCS categories to provide isolation between containers. We can expect Docker to further grow and embrace more SELinux access controls, and Red Hat's approach might become the standard in the near future. For instance, an Nginx process running inside a Docker container is shown to be labeled with the svirt_lxc_net_t type and an MCS category pair. We've had enough of talking. Let's get our hands dirty with some commands. I've already installed Docker by running the command m-install docker. Now let's start it with the command sudo systemctl start docker. You can check the status of its service by running the command systemctl status docker.service. So, you can see the status for Docker container on my machine is active. Nice. Let's exit and try out the next command. ps-wwc nginx-o label command. As Docker does not use the same concept of images as higher virtualization technologies, those supported through libvirt, the image-related types such as svirt image t and virt content t, do not apply to the svirt lxc net t type enforcement. Instead, host-level file types are used with only the svirt sandbox fillet type being explicitly used for resources that can be fully managed by a container. Unlike libvirt, Docker containers are not defined through XML files. Changing SELinux controls on containers is handled through the command line. A strong feature of Docker is the ability to modify the capabilities of a container. Capabilities define coarse-grained authorization on Linux and are used by Docker to limit what software running inside a container can do. For instance, shutting down the host, which is a kernel-level instruction, is not allowed by default from within a Docker container. By default, Docker already limits the capabilities that are active for a container. Administrators can further fine-tune the capabilities, or even decide to only enable a given set of capabilities directly. By limiting container capabilities, kernel exploits can be further thwarted and container breakouts can be contained. To remove capabilities, use the -cap-drop option of the Docker run command. Nimis or Alpine Nginx is the name of a publicly available microcontainer that hosts Nginx and is used here for example purposes. Let's type the command docker run -cap-drop mknod -name nginx-d nimis /alpine nginx. Click enter. So wait for some time while it pulls the repository registry. Let's run the next command, docker ps. As you can see, it returns the status, image, ports, when it was created, and the rest details. Here's our next command, ps-efgrep boot.sh. Similarly, try the third command, pstree-a ps 2728. You can use the PS tree to see the resulting processes that are started. With the -s option, it will even show which processes have switched namespaces. The capabilities of this running container can be checked through the status sudo file for the given PID. Here's how we do it. Type grep cap/proc/2743/status. As this is a bitmap of the capabilities, capf shows the effectively active capabilities. It might be hard to deduce that the mknod capability is not active. We can use the pscap command, which is part of the libcap ngutils package on RHEL, to show the current capabilities in a more human-readable format. We now try the pscap command. It will ask if you want to install the package. Let's say yes. So here are the capabilities currently active. There are a few SELinux booleans only on RHEL that influence the supported capabilities, but these booleans apply to all containers running on the same host. These are listed on your screen. A more fine-grained approach is to use separate SELinux domains for individual containers that require additional capabilities to be set. Docker has a nice feature called volume mounts. When used, parts of the host file system are mounted into the container's file system view, allowing the container software to read or even write resources to a remote location. This is particularly useful for containers that need to persist data across container reboots, as containers by default do not persist their changes in their own environment. Every time a container is started, it's pristine again. Let's look at an example that mounts a host's srv/web/tomcat1 location into a container's srv/web view. Run this command. So, with SELinux enabled though, volume mounts might not be readily accessible by the container. After all, the container is running within a confined domain, which might not have write access to this location. Administrators can relabel the resources manually, but luckily Docker has this covered. When adding :z to the volume mount, Docker will relabel the content with the svert sandbox file T type, which is a type that svert containers have full manage rights on. For this, let's run the next command. As you can see here, we just add :z and change the container name. When adding : with an uppercase Z to the volume mount, Docker will not only relabel the container with the svert sandbox file T type, but will also assign the MCS category set of that particular container. As a result, the files will only be manageable by that particular container, and not be reusable by other containers. Let's see how it's done. We just replaced the previous command just by changing the lowercase z to uppercase Z. Also, we changed the container name. If you want to enable a location, but with read-only access, administrators will need to relabel the files manually. Docker has no option yet for automatically relabeling content for read-only use. Now, the svert technology supports modifying the default contexts. Docker does not hard-code the domain types and resource labels, but obtains these values from an SELinux-provided configuration file, LXC contexts, which is stored inside the contexts directory. The example on your screen shows the default contents of this file, and defines the labels used for various purposes. Administrators can modify these defaults, but they must be aware that these files are part of the SELinux policy packages and might be overwritten when an updated policy is deployed. Therefore, it's advised to stick to the labeling features of Docker itself. In this section, we looked at virtualization and the risks associated with it. Also, we had a look at MCS confinement. Next, we covered how libvirt architecture. Finally, we looked at Docker, a popular container technology, and how here too svert can provide container confinement both from an access control approach as well as isolation. Here too we looked at how the various SELinux controls can be fine-tuned by administrators, ranging from defining the domain label of a container up to volume-mounted SELinux labeling. In the next section, we'll look at another pair of SELinux-aware technologies, dbus and systemd.